All right, workout problems for lesson 30. Here, workout problem number 5. So A, based on the picture, what's the direction of the angular velocity of the cylinder? We have our cylinder, it's rotating this direction. So based on the right hand rule, as it's rotating, if we put our fingers in curl our fingers in the direction of that rotation, our thumb points into the paper in this case. So we normally annotate that with an X. So if you think about an arrow, that would be like the feathers of the arrow because the arrow is pointing into the paper. So we can say into the page. All right, so for part B, what is the direction of the angular momentum or the angular acceleration, sorry, at point A and at point B? So we'll do A first. So at A, our object is still rotating in this direction, and we know that it is going to be speeding up. Acceleration, because it's increasing, is going to be in the same direction as the angular velocity. So we have alpha here is same direction as omega. So alpha is into the page. Now, for B, we know that it's going to be going uphill here. This is going to go up to B. So as we are gaining potential energy, we are losing kinetic energy. So that object is going to be slowing down. So while it is in the it is still rotating, and our angular velocity, excuse me, is going into the page. What we wind up with, because it's slowing down, that alpha is the opposite direction of omega. So that means that alpha is coming out of the page. All right, problem 6 for the lesson 30 handout. Take a look. We've got this wheel spinning around. We're given both the angular velocity and angular acceleration vectors. So we're going to start by just creating a plot of those. With this being north, east, south, and west. So if we take our angular velocity vector, it says it's pointing towards the east. So that's our angular velocity initial. And then if we take our angular acceleration, we're pointing 68 degrees west of north there. So there's our angular velocity. The other way that we can measure this, and it makes it easier for our calculations, if we take the angle all the way to the x-axis, so that would be 90 plus 68 degrees. Now, once we have both of those, it's going to be a little bit easier for us if we break this up and we say, all right, this is going to be, we're going to call that our y-axis. We're going to call this our x-axis, even though we have them labeled as northeast, south, and west. So our angular velocity vector is 140 rads per second in the I hat direction then, and our angular acceleration vector is going to be 35 times the cosine of 68 plus 90 in the I hat direction, right? That's just taking basically our, let's change colors here. We just look at, our x and our y components of that vector, that's where those are coming from. So if we find our y component, that's going to be 35 sine of 68 plus 90, as measured from the x-axis there in the j-hat direction. Now, once we have both of our initial velocity and our acceleration, we can use kinematic equations. So omega final equals omega initial plus acceleration times time to find our final angular velocity. But we do this, we have to break it up into components just like we did when we were doing with linear. So our initial angular velocity in the x direction is 140 per second, plus our angular acceleration in the x direction, 35 times the cosine of 68 plus 90, and then all that times 5 seconds. And I should mention this is per second squared, goes in there. That's the units on that. So when we solve all of that out, what we wind up with is a negative 22.3 per second. So that's radians per second again, I hat. Now we're going to do that in the y direction as well. And that time we have 0 initial velocity in the y direction plus a 35 sine of 68 plus 90 per second squared times 5 seconds. When we solve all that out, we get 65.6 rads per second in the j-hat direction. Now in this particular case, it asked us for the magnitude and direction. So instead of leaving it in I-hat, j-hat components, we have to go all the way through to find magnitude and direction. So that magnitude of omega final is going to be the square root of omega x squared, which is negative 22.3 squared, plus omega y squared. So that'd be 65.6 squared. And when you do that calculation, you wind up with 69.2 rads per second there. And then for our angle, we take the inverse tangent of negative 22.3 over 65.6, and that winds up being 19 degrees west of north. So our final two answers are those two. All right, problem 7. I've got a child running and jumping onto a merry-go-round. So if we draw this out, we have our merry-go-round here. Child's going to run and jump in, and we'll have the kid land on the merry-go-round right at the outside edge. We know the radius from the center to the outside. So our R from there to there is 1.5, and we know all the masses. So we were trying to find angular momentum. So our angular momentum is equal to R cross P, because we have this child running in at a straight line, so it has linear momentum when it jumps on rather than already having some angular velocity. So that's why we'll use P. And if we break this down a little bit further, we'll get R cross mv, and once again, that just goes to R mv sine of theta for our magnitude. So if we plug all these in, what we're going to get is 1.5 meters times the mass of the child. This is the thing with the momentum coming in. So this is 31 kilograms. And our velocity is 1.2 meters per second. And then the angle between these two, if we look over at our diagram, if this is the momentum vector and this is our r vector, then the angle between those is 90 degrees. So sine of 90, and that goes to 1. So when we solve all of that out, we get our angular momentum to be 55.8 kilogram meters squared per second. However, angular momentum is a vector, and so we use that right-hand rule, put our fingers in the direction of R, cross them in, or curl them into the direction of P, and we find out that that is into the page. All right, for problem 8, we have this weather station. We've got this wind vane, and it's going to be spinning as the wind hits it. We're trying to find the angular momentum when it's rotating at a certain speed. So angular momentum, in this case, because we have a spinning object, is going to be I omega. We have omega. We're just going to have to convert to radians per second, and we're going to have to find I. So first off, finding I, we'll do that down here. So I, right, we're going to treat these as point masses, and so I is just mr squared for a point mass, but in our case we have 4 of them. So if we just plug these numbers in, our mass is 0.12 kilograms, and our radius is 32 is the length of the rod, so that means that the radius here is going to be 16 centimeters. So that would be 0.16 meters. That gets squared, and then when we solve that out, we wind up with 0.012 kilogram meters squared. For our I, we'll take that back up, plug that into our equation. We get 0.012 kilograms per, or times meters squared for I. Now for omega, we have to convert from revolutions per second to radians per second. We know 1 rev is 2 pi radians, and so when we perform that calculation, we get 24 pi per second. That can now come up here, and what we wind up with when we multiply that out, 0.93 kilogram meters squared per second.